Hey everybody, we're going to be talking about Notebook 14 today. So take a moment and get that opened up from D2L course calendar. And I'll assume that you've paused the video if you needed to get this open. What we're talking about today is the one sample t-test. Now, kind of jumping to the bottom, this is a whole lot like the bell curve. So the t-tests are based on a very similar distribution to the bell curve or the normal distribution. And so the very earliest hypothesis tests use the bell curve. But it turns out that the t-tests are a little better, a little more robust, and especially for small sample sizes, right? So small samples, we get more accurate p-values with the t-test. So this is the modern version that we use for these hypothesis tests that we used to use the normal distribution for. So we have some graphics that show the t-distribution is nearly identical to the normal distribution, and let's take a look at that. Okay, so here I am inside Notebook 14. Hopefully you've got this open, and I'm going to run the initial code block. And yes, it's run, and we're open and running. And like I said, the very first thing we see is this t-distribution graphic. So first notice the red line, that is the bell curve. And then the green line is the t-distribution. Now notice that the slider going backwards and forwards there is called degrees of freedom, but that's basically um, about the same as the sample size. So for small samples, we see that the green or t-distribution is a little different. But as the sample size increases, these two distributions are very, 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 very close to each other. So the green distribution has just been corrected, especially for small sample sizes, to be more accurate than the bell curve. And for large sample sizes, it works exactly like the bell curve, which is why we're allowed to use the t-distribution and why the first several hypothesis tests we show you are going to be based on this t-distribution. Okay, so the first hypothesis test we're going to take a look at is, do students take 5 classes per semester on average? Okay, so when we talk about hypothesis testing, we're talking about the process that scientists use to find evidence for trends and relationships within a data set, right? So what we've looked at so far, we've looked at associations. And if we want scientific evidence for a certain relationship, um, then we use a hypothesis test. And so the steps, we do have to set up the hypothesis test. We simulate the test statistic. That's where the computer comes in very handy. Every single hypothesis will generate a p-value. Okay, now this isn't exactly true, but with some assumptions, basically the p-value is the probability that the null hypothesis is true. Okay, so that's why we reject the null if the p-value is small. If that's the probability that the null is true and the p-value is really small, we reject the null because it's just not likely to be true. And then we have the other option, if we have a larger p-value, is that we fail to reject the null. Okay, and then the last step is to write our research conclusion, and we're going to say what we have evidence for. We're going to have evidence for the null hypothesis or for the alternative to the null hypothesis. We'll start with the first example. On average, do students take 5 classes per semester? Okay, and you're going to notice that when we get this class data file loaded, one of the things that we're going to have is, the number of classes. Now, assume the thing is at UNG, most of our classes are 3 credit hours. So I do know there are other classes that are more or fewer hours, but basically we're taking the number of classes and assuming that that's about 15 credit hours, and that's the average. Okay, so there's our hypothesis. So H sub 0 is how we identify the null hypothesis. And what's the null hypothesis? Hey, students take 5 classes per semester. So there you go, mu equals 5. What's the alternative? Well, if the average number isn't 5, it's some number other than 5. So we're using the not equal to there. All right, so pretty straightforward in how we set up the hypothesis. The next thing, sorry, the next thing is the code and results. We'll jump into the code in just a second, but I want you to notice this is the name of the table, and we're doing a dot column. Why do we do dot column? Because the thing that needs to go into the t-test is an array. So we turn this number courses column into array data, and the pop mean equals 5. That's this. We're telling the computer what the null hypothesis is, so it knows what value to compare to. Okay, and let's just leave that there for the moment and take a look at the code that will accomplish this. All right. Sorry. Okay. So again, here's the classes. We're just loading the data set. And you can see that this num courses column is where we're going to go to get the data. All right. So favstats is a well, it provides a bunch of statistics for us, right? The average and standard deviation and the 5-number summary, which is the min, Q1, the median, Q3, and the max. Okay. And notice the sample size is 298. All right. So, and this is the average number of courses appears to be about 5.01, 5.02. Okay. So here is the t-test. Now notice that we've imported this slightly differently. It should work either way. What you'll normally see is the stats.t-test, but we've imported this slightly differently. So just letting you know, if we go back and look at what alias was created, we did import just the t-test without having to, it's in the stats, excuse me, the scipy.stats module, but we've imported this specific function with its name. But if we import it differently, other places in the class you'll use stats.t-test. Okay, notice we have the comma, population mean equals 5. I'm going to point out this because later it turns out that we don't need the pop mean equals. It's one of those tests that has only really one option for adding something. So I can get the results that way. I just ran that. It turns out that if I just type in 5 rather than pop mean equals 5, I get the exact same thing. Why am I telling you that? Well, it's one of those time saving. It doesn't save a ton of time, but it saves a little bit of time. And if I don't put in the pop mean equals, if I just put comma equals 5, it interprets that to be, oh, that's the null hypothesis number that I need. Okay? And then this is the information that spits out, which you'll notice I have recorded here. Our test statistic is around 0.414. And our p-value is 0.68-ish, okay? But notice, remember that since the lady and the t, we've always used this traditional value of alpha equals 0.05. So if we aren't given a value for alpha, we use 0.05. And p is much bigger than that, right? P is 0.68, so p is greater than alpha, so we fail to reject the null. In other words, we don't have any evidence. We have zero evidence to suggest the average number of courses taken is not 5. Now, I understand the double negative is a little awkward, but it is how statisticians report this. They say there is no evidence that the average isn't 5. And you say, well, doesn't that mean that the average, that the evidence says the average is 5? Well, again, that's not how statisticians say it. They say there's no evidence, it's not 5. But you can think of it this way. When the p-value is small, we have evidence for the alternative. And when the p-value is larger, right, and sometimes we say we have evidence for the null, but we have no evidence the null is wrong, right? Well, if we have no evidence the null is wrong, then maybe we think that it's true. And again, it's not quite correct to say that, but that's the idea that we want to get across there. Alrighty. So when we look at this next example, we're going to see, do students get at least 8 hours of sleep per night? Okay, now the way we're going to set up this hypothesis is actually the alternative is going to be that the average number of hours of sleep. So this is a lowercase mu. So that's for the population average. And so our null hypothesis is that on average, students get 8 hours of sleep at night. Our alternative is going to be mu is less than 8. Why? Because we're testing the alternative specifically, hey, do they get less than 8? Why? Because if we don't reject the null, we'll have evidence that they get at least 8 hours of sleep per night. Okay, so we will test this hypothesis, and I just want you to notice it's the same thing. We're going to run just t-test. Again, we're going into the classes table and creating a column for sleep hours so that we actually are, look at, that's the variable that we want to look at. So that's the column name. And notice that they left out the pop mean equals. They're just putting in 8. So we do know the value of the population mean for our null hypothesis. Okay, and let's go do this. So first off, in Notebook 14, we actually get some notes about how this works. And so the alternative hypothesis, right, and I've been calling it the null hypothesis number, but we use that. 5 and 8 are the two that we've done, right? Well, our null hypothesis always has to specify a number. So we're guessing what the average of the population is. And that's what mu sub 0 equals. And then our alternative hypothesis for a t-test can either be not equal to, which is called a two-tailed test, or one of these two strict inequalities, either less than or greater than, and those are one-tailed tests. Okay. And you're not going to have to do this manually. That's what full disclosure bit is. But this is how we calculate t. And degrees of freedom, I told you, are approximately equal to sample size. So in this case, degrees of freedom are n minus 1. N is the sample size. Okay, and we use the degrees of freedom to find the correct t distribution graph so we can get accurate p-values. All right. So let me pause for just a moment and I'll get ready for the next example. So the second example is, do students, wait, I'm sorry. Yeah, wait, do students get at least 8 hours of sleep per night? Right, I'm sorry, that's the one we're doing. Okay, and so here's the fave stats for the sleep hours, and notice that the average number of hours is a little less than 8, right? So 7.3, 7.4 hours. Okay, and then here is the code, right? T-test, we're doing the same thing where it's the classes table, and we use dot column because we need array data to go inside the t-test. And we're telling it, hey, the mu sub 0 from the null hypothesis, that number we need, mu sub 0, is 8, right? And when we run that, sorry, let me get back here where we can see it, we do get the test statistic of negative 8.3, and we get a p-value. Notice that we've switched to scientific notation. Because even though this number starts off 3.6, because it's scientific notation, right, that times 10 to the negative 15th means that this p-value is very, 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 very close to 0. All right. So watch for that when your p-value is a percentage, so it's going to be between 0 and 1. When it starts with an integer before the decimal place, check the end of the number because almost always that means that we've switched to scientific notation. So let's look at reporting this out. Sorry. There we go. So I've included those statistics. I have rounded a little bit. And what do we get? Well, now notice that the p-value is very, 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 very close to 0. So now we know that p is less than alpha. Therefore, we reject the null, right? Why? Remember, the p-value is the probability the null is true, and if p is very small in here, we essentially have a p-value of 0. Now, I know it's not actually equal to 0, but it's really, 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 really close to 0. And since the probability that the null hypothesis is true is so low, we're just saying, hey, reject it. Okay, that's why we use this terminology, reject the null, because it's just very unlikely to be true. What's more likely to be true is the alternative. Okay, so now we have evidence that students get fewer than 8 hours of sleep per night. Now the graphics here are going to create a picture of what's going on, okay? And notice that the p-value is so small it's not even visible. Up above in example 1, they showed us some p-values, and there's a red line down here. We'll talk a little bit more about that in the future. By the way, the one-tailed p-value is the two-tailed p-value cut in half. Why am I using a one-tailed or two-tailed p-value? Well, let's go back here. When I use an inequality, it's one-tailed. So the not equal to is two-tailed, two-tailed. And then the less than or the greater than, sorry, I did that backwards. The greater than or less than, these are one-tailed tests. And for the one-tailed tests, we do have to cut the p-value in half. It's mathematically correct to cut the p-value in half. So let's go back here and you see that it is 0.5 times the p-value. It doesn't matter that much, and I didn't include it above. Why? Well, because the original p-value was so close to 0, so being even closer to 0, we still would have had the same reject the null result, okay? And so what do we report out? As we said earlier, just a second ago, since the mean of the sample was about 7.4 hours of sleep, and reject the null, that's the same thing as your notebook is using when it says statistically significant. Those are synonyms, reject the null and statistically significant. And the notebook is using p is even less than 0.001, which it is. It's very much less than that, close, almost virtually 0. Okay, and so we do have scientific evidence now that students get less than 8 hours of sleep per night. And here we can see a box plot of the situation. All right, and while there are outliers, sometimes students do get more sleep than, well, even more than 10 hours, those outliers. And there are students who unfortunately get very little sleep or way less sleep than some of the others. But notice that the average is the gold triangle, right? And the red line. So the mean and the median are close to each other. All right. And they're both significantly less than 8, it appears. But we have scientific evidence that the mean is significantly different, significantly lower than 8. Okay. And now your book goes through, well, hey, do students get less than 7.5 hours of sleep per night? Notice that this is exactly the same as the hypothesis above. The only thing different is that the 8 is changed to 7.5. And notice that the p-value initially looks bigger than 0.05, but remember this is a strict inequality here. So we cut the p-value in half. And when we look at this p-value, you can see, oh, that is less than 0.05. And this they're showing you, we're shading under the bell curve. The area shaded is about 3.5%, which is less than 5%. So we reject the null and we find, again, statistical significance that students, they don't just get less than 8 hours of sleep. It appears that we have evidence now that they get less than 7.5 hours per sleep at night. And then again, here is the distribution of hours of sleep. And now we're ready for our third example. We'll be looking at a different data set, And notice that it's the baby.csv data. We've looked at this data before, but the question is, do babies born to mothers that don't smoke tend to weigh more than 118 ounces? So basically, this is an older data set, but it's one of those data sets that was trying to assess whether or not smoking during pregnancy might be harmful to the fetus. And so they're using the baby's birth weight as sort of a proxy for how healthy they were. Back then, it was thought that, underweight babies were less healthy. And now we know that the babies can grow too big and can cause a problem with um, labor and delivery in that way. But basically, we're saying, hey, we'll use 118 ounces as our population average, and we're checking to see if the babies born to non-smoking mothers are more than that. And like I said, it's a general proxy for the health of the child when born. Okay, sorry. And again, we will be using the exact same stats.t-test. We're going to use column. We need array data, and the 118 is our population mean. So let's jump over. Sorry. And okay, so notice that we're using a different table, and then non-smokers, right? We're taking, well, here, we've seen this before, but let me just comment those out and you can see. Let me do a show. Wait, let me do, oops, sorry. Births.show. You don't have to do this. I'm just going to show you what the table looks like. Let me do show 5. All right. So we have all these values for each of these babies born. So we're looking at the birth weight of the baby at birth. Okay. And we're looking at maternal smoker is set to false, right? So these are all the non-smokers. All right. So I just wanted you to see what we're doing. So we're creating this array called non-smokers. And it's just from the births table where the column maternal smoker is false. And then what's this? We're taking a random sample. Excuse me, take NPA range. No, we're not taking a random sample. We're taking, I'm sorry, that's counting from 1 up to 700 by 20s. Okay, so that's taking a sample of them. Okay, and here's the hypothesis, just like I showed you on the other slide. And so here we go. Here's the fave stats. Sorry, I've got to execute this code now that I've taken the comments out. And then the fave stats is showing us that the average is about 124 ounces. Okay, well, that's interesting, which means that therefore the p-value, ooh, it's not quite small enough. Oh, but again, we were testing a one sample hypothesis. So we're going to cut the p-value in half. And now our p-value is 0.03, right? Which is statistically significant. We do reject the null. And babies born to mothers that don't smoke we do have scientific evidence that their average birth weight is greater than 118 ounces. And again, the situation is shown in the box plot. You can see once again the mean and the median are nearly identical, and the mean is significantly greater than 118. So the next, or the little bit of code here at the end of the notebook talks about creating confidence intervals. Okay, and basically this is how we estimate the average of a population. So for example, there are about 7,500 students on the Dahlonega campus, and let's say we survey 200 of them about perfectionism, and we can estimate the average level of perfectionism for a UNG Dahlonega student by using the sample statistics that are in our research, okay? And these confidence intervals have a percentage, like we'll refer to one of the most common ones is the 95% confidence interval. And what does it mean? Well, we're going to use it for an estimate, okay? And what does it mean? It means that we are 95% confident that the population average falls within the interval. Okay, so how does this work? All right. Again, here's the formula, but you won't have to do this by hand. Okay. And here is the plot that's going to do it. What are we looking at? Here, they're just showing a graphic of what we're doing. So we're calculating an interval that captures the middle 95% underneath this curve. Okay, so we want the middle 95%. Okay, which means we're leaving 2.5% above and 2.5% below, so we have the middle 95%. Okay, that's lovely. They talk about some of the different confidence levels that we use and how that changes the T statistic, the T star statistic that we use. And here's the thing, as the confidence goes up, T star goes up. And why? Well, we get the law of large numbers, right? Larger samples are generally more reliable when it comes to estimating the mean. All right, and again, we'll cover confidence intervals in a little more detail later. This is just showing you how they're coming by these values, okay? And then they actually take this on and they show the first classes is the number of courses. If we just estimate the number of courses. And by the way, this is really cool code. It's just given to you. This will work for any confidence interval, any 95% confidence level, and you can change the confidence level down here. And here we go. Boom. What do we get out? We get a point estimate of what the sample mean is, and we get an interval. So we know that the number of classes taken by UNG students is between about 4.94 and 5.10, I guess. And so we know that the true mean will actually be inside this interval about 95% of the time. Why? Because we did a 95% confidence level. Okay. And there's another one right below it. Oh, excuse me, I'm sorry. This is the graphics that show the red down here is the confidence interval. That's where we think the mean is. Why? Well, because this is the simulation, right? So there's some histogram in the background here, right? Where we've simulated the sample mean, sorry, and I'm drawing a very bad histogram, but there is some histogram in the background where we have simulated the sample mean. And so the red line down here, let me get rid of all of my ugly drawing, and you can see the sample mean is shown, excuse me, the possible values in the 95% confidence interval of the 95% confidence interval is shown. All right. So the confidence interval, the 95% confidence interval for the number of sleep hours is shown in red. And we're just giving you a couple of examples to see how this works. Okay. And then we have the 90% confidence interval shown, sorry. Get back up here. This is for the sleep hours estimate. And you can see, I hope, that the null hypothesis was guessing that the population mean was 8. And it turns out that the population mean is more likely to fall inside this interval. So it turns out that we can use confidence intervals as hypothesis tests. Okay, let's take a look at that. So I've just gone down a couple of code blocks to where it says using simulations. All right. And what we're going to do is we're going to use the bootstrap method to simulate the number of nights, excuse me, the number of hours of sleep per night that students get on average. Okay, so we're going to resample over and over and over and over and over our original data set, and we will end up with a simulation that we can use to test our hypothesis. Okay, so what's going on here? Sorry, I was trying to hit Shift Enter. There we go. What is going on here? Well, we're using this sleep hours variable, and we're creating a bunch of means. Remember, we want to take samples thousands and thousands of times, and each of the samples will find the mean. We're going to do this 5,000 times, and we're calculating one sample mean, and we're adding it to the end of this array called bunch of means. Okay. And here we go. Here is everything that goes into it. Excuse me, these are the results. Okay. And so we find that the average of all of the means is 7.36. But now what's nice about this is we have this, estimate, this bell-shaped curve is an estimate that's centered on the average number of hours of sleep college students get at night. Okay, so that's good. And so what do we do if we want to test this hypothesis? Do students get less than 7.5 hours of sleep at night? Okay. And so here they're changing the cutoff. Remember, or if you notice, they used 7.8, excuse me, they used 8.0 up above. We're using the 7.5 right here. Okay. And now it does appear that it's a little more possible for the mean to be in this confidence interval. All right, but this is the p-value approach where we only found that 3% of the time um, the mean from the sample actually turned out to be up here above our null hypothesis. Okay, and so we're looking at the percentiles. So we get the 90% confidence interval, and notice this, that 7.5 is not in the interval. The biggest number in the interval, the right-hand side of the interval, is 7.48, which is less than 7.5. So this is where our hypothesis test is happening. Okay. And you can see in the drawing here, right, that the red dot is out here to the right. The gold is showing the confidence interval, and the red is showing where our null hypothesis value of 7.5 is. This means we can reject the null. This means that we have evidence that the value 7.5 is not in the confidence interval, and therefore it's likely that the null hypothesis is not true, right? So let me go over this on the slide just to help bring it together. So it turns out that we can use confidence intervals to do hypothesis testing. Okay, so normally we do, if alpha is 0.05, we create a 95% confidence interval. So the confidence percentage is 100% minus alpha, or 1 minus alpha switched to a whole number percentage. Okay. And with the traditional hypothesis test, we have this criteria. If p is less than alpha, we reject the null. Okay, the confidence interval is a little bit different. We look to see whether or not the interval contains the population mean. In the previous example, it was 7.5, but 7.5 was not contained in that gold confidence interval that was shown. And if the interval does not contain, if the confidence interval does not contain the population mean, does not contain the mu sub 0 number from the null hypothesis, we reject the null. Okay, so the simulation happens in the same place, except rather than doing a simulation inside that t-test and getting a p-value, instead, the simulation happens where we bootstrap that distribution and get the confidence interval. And then we check to see if mu sub 0 is inside the confidence interval. And if it's not, then we reject the null. And I also want to mention this if we have a one-tailed hypothesis. Okay, so this works for two-tailed hypothesis where the confidence is 1 minus alpha, right? So again, this is for two-tailed hypotheses, which is a not equal to, all right? But our one-tailed hypotheses are less than and greater than. So if I want to test sorry, that's really bad. Just trying to draw greater than. There we go. Less than or greater than are one-tailed hypotheses. And what does that mean? Okay. Then the confidence percentage is 1 minus alpha over 2. What does that mean? So if you want to test an alpha of 0.05, you divide that in half. Half of 5 is 2.5. Okay. And then I do 1 minus 2.5, which is 97.5%. And that means that if I want to do a one-tailed hypothesis and alpha equals 0.05, then my confidence would actually be 97.5%. Okay, so that, again, the last bit about confidence intervals is a little bit of a spoiler alert, a little bit of preview of coming attractions. And hopefully this has been a good introduction into how that works.